All right, thank you for coming to Papers We Love LA. This is the first one we've had in a while. Thank you to Jake and Brainium for hosting and for giving me the opportunity to speak. My name is Daniel, and we're going to talk about a paper by W.R. Thompson on the likelihood that one unknown probability exceeds another in view of the evidence of two samples. So first thing, on the evidence of two samples sounds kind of ridiculously small, doesn't it? So that doesn't sound like a lot of samples. Another thing is, the likelihood that one unknown probability exceeds another. So two unknown probabilities, and we want the likelihood. Man, that also sounds like another probability. So we're measuring two probabilities with some third probability, something like that. This paper appeared in Bioinformatica in 1933, and so it's not the typical thing we do for Papers We Love. Typically, we do something for something in Comp Sci or something at least a little bit more recent, and this is 1933. So I think I promised applications to machine learning, so they're got to be in here somewhere. So let's take a look. So let's talk about the problem that this paper purports to solve, okay? So the problem we have here is medical experiment design. Thompson was a medical researcher at Yale. And it's a basic, typical scenario. You have two potential treatments, call them A and B, and you're not certain which treatment is better in some observable sense. So you can say better as in you pick some trait, like say hair loss, something like that, and you want to say maybe prevent hair loss. You pick some criteria, and then you say, okay, now I'm going to measure better by which one prevents hair loss, more frequently. So something like that, but you pick some criteria for which you're going to measure better. And how do you decide which patients get which treatment? Two competing treatments, you don't know which is better. How do you decide which patient gets which patient? A typical example comes up when we do medical research that has placebos versus versus active ingredient drugs, actual medicine. And you might say, oh, well, why are we comparing a medicine against a placebo? And this is simply so that you can tell that the medicine does something, really. So these treatments don't have to be something like two different medicines. One could be a placebo, one could be a medicine, but you generally have two different groups of people that you're treating differently somehow. Maybe the people don't know what group they're in, but whatever. Two different groups of people that you're treating differently somehow. And you want to see which treatment is better by your criteria you care about. So here, this problem naturally has some competing goals that you have to balance. Let's suppose that we start out thinking that treatment B is better than treatment A, and we start out, say, at 75% confidence. We're 75% confident that treatment B is better than treatment A. How did we get that confidence? I don't care right now, just run with it for a moment. We have some competing goals when we decide what treatment to give to what patient. First goal is exploration, in which we hopefully want to improve this confidence. If treatment B really is better than treatment 1 in some objective sense, then we should be able to get this pretty close to 100%. But then we have a competing goal of exploitation. If we think that treatment B is better, why aren't we giving treatment B to everybody? Don't they deserve it? So you have those competing goals. So let's look at some solutions. Two kind of obvious solutions. All patients get treatment B. Another solution, half get treatment A, half get treatment B. So often this is what you'll see in clinical trials. You say, okay, half the patients are going to get placebo, half the patients are going to get the medicine. And then after a certain while, when I guess the doctors are satisfied, they say, okay, we're gonna stop splitting people up, and then everybody's gonna get treatment B if we think it's better at the end. So the problems with these, when you say all patients get treatment B, if that's what you decide, then you're just done. You've given up increasing your confidence. You're just done. And yet, here, if we had 75% confidence, it's still a 25% chance we're wrong. And I don't know about you, but 25% chance is a pretty big deal. 25 things that are 25% chance of going a certain way go that way 25% of the time. There's actually a lot of the time. I say that, and that's kind of a frequentist approach. So you say, okay, 25% of our patients this treatment's not going to work. But that's not what it means. The frequentist point of view doesn't actually work here, because you're giving all patients the inferior treatment if you're wrong. Not just 25% of them, but all patients. So there's a 25% chance that every patient from here until the end of time gets the wrong treatment. Splitting people up 50-50. Is this ethical? If you think that treatment B is better, shouldn't you be giving people treatment B? And when do you stop? When is your confidence high enough? Do you wait until your confidence is 90%, 95%, 99%? All of those are arbitrary numbers. Why not 99.9? Why not 80? So when do you stop? So this brings us to the paper that we're going to look at today on the likelihood that one unknown probability exceeds another in view of the evidence of two samples. Let's actually take a look at the paper real quick. So we have it in I think I said bioinformatica. It's biometrica. Let's see. Department of Pathology. So this is not a medical doctor, but someone who I think works a lot with medical doctors. I'm not quite sure what Dr. Thompson's credentials were, PhD or MD. But either way, he's fairly good at math. He's so good at math that obviously is one of his favorite words. So let's take a look at this. Obviously, we may write. Okay, Dr. Thompson, thank you. If you look at that and you kind of go, okay, what is going on here? I don't blame you. None of this is obvious at all to me. But we have some math. We'll go into this in more detail here. We have Pascal's triangle. Okay, I know what that is. And let's see, we'll keep going. We have these, we have this psi function, which is going to be important. We have an n function and a d function, which are both going to be important. We'll come back to. And we have this table of numbers. What do these numbers mean? We'll get back to that in a minute. And why it looks like there's a lot of work going into doing this. So what is behind all this work? We're going to answer that. Okay. So back here. What is the purpose of Dr. Thompson's paper? So he starts out in the first paragraph saying, this paper is not centered upon the interpretation of particular data. So I get the idea that things in biometrica are usually about a particular study. And he says, this is not about a particular study. This is about a general interest in problems of research planning. So that's the problem we had before. How do we design a medical experiment? And he goes on to say, there can be no objection to the use of data, however meager. Think about the title, on the evidence of two samples. There can be no objection to the use of data, however meager, as a guide to action required before more data can be collected. This is a little bit iconoclastic because you say, okay, I'm going to base a decision on a small number of samples. That is not really accepted practice. So he goes on, says serious objection can otherwise be raised to an argument based upon a small number of observations. So serious objection can be raised when you base an argument on a small number of observations. But he goes on and says, indeed, the fact that such objections can never be eliminated entirely. You never get the confidence up to 100%. So such objections can never be eliminated entirely, no matter how great the number of observations, suggested the possible value of seeking other modes of operation than that of taking large number of observations before analysis or any attempt to direct our course. So that last phrase is the typical modus operandum. Okay, we're going to just split our people into two groups. We're going to split our patients into two groups. We're going to collect a shitload of data, and then we're going to go over that data, and then after we look at that, then we're going to decide what to do in the future. And he says, no, because you say you're doing this to solve the problem of small sample size, but how much is a big enough sample? This is arbitrary, right? So he says there must be some other way, there must be some way that we can analyze small amounts of data and somehow turn those into decisions that allow us to guide our experiment process. Okay, so this is a little outline. So section 1 of the paper. So section 1, this is what Thompson thinks researchers should be doing. Two things. So instead, let me go back a little bit. Instead of doing the modus operandum, which is the last sentence here, get a ton of observations and then analyze it, this is what we should be doing. Select an option proportionally to our belief in the benefit of that option. To say benefit, I guess Thompson is a utilitarian or something. So we have 3 mutually exclusive options, I'm supposing. They don't necessarily have to be medical treatments, but each of those options has a certain number of expected utils. You know, how do we expect that? I don't know, from past observations, let's say. So we're going to select an option proportionally to our belief in the benefit of that option, you know, how much utils it gives us. So here we add these up, there are 400 total utils. So we say, okay, this one is 204 out of 400. We want to choose X with 50% probability, choose Y with 37.5% probability, choose Z with 12.5% probability. Now, in addition to this first one, Thompson says that we, researchers, should continually update our beliefs rigorously using Bayes' theorem. Now this is a little weird for a lot of people because they say, okay, a belief is necessarily this kind of ephemeral, kind of personal thing. But Bayes' theorem actually gives us a way to measure our belief in light of the data and update our belief when we get new data. So here's a Bayes' theorem with loaded terminology. So we have some probability that our belief is accurate. Say earlier we had said 75% belief that treatment B was better than treatment A. If we're able to calculate the probability of making an observation assuming that our belief is correct, so the bar here in probability means assuming that the other guy is correct. Assume our belief is correct, calculate the probability of getting the observation that we ended up getting. And divide that by the probability of getting that observation just out in the open. This fraction here gives us a coefficient that tells us how to update our belief given that we got some observation back. The idea is probability of belief is given, like our 75% belief that treatment B is better. The probability of the belief given the observation is very difficult to calculate. We don't know how. Oh, but presumably it's a lot easier to calculate something's probability if you just assume your belief is true. Now, normally, assuming your belief is true and then doing stuff, acting on it, is not normally a great course of action. But here, we're using it to update our belief, and the reasoning holds for, if you accept that kind of, if you accept that interpretation. So these two things, he's saying researchers should do. Now, he never gives his associated so that. So when you make a prescriptive statement like, we should be doing something, that always comes with what is the goal behind this should? So it's a question, and Thompson doesn't answer that. So I'm going to kind of put words in his mouth, but the idea I get is that Thompson is kind of a utilitarian, and he does want the maximum number of utils in the world. And in the sense of this paper, he wants the maximum number of patients cured. And he makes some assumptions in order for his algorithm for choosing options to help the most people. There are some assumptions. One assumption is that you have an infinite stream of people that you're going to help afterwards with the knowledge. So that's important. But the associated goal here of these should statements is that we want to, assuming that we're always going to have more patients, we want to cure the most people. Okay, section 2 of the paper are the math bits, okay? So in section 2, Thompson describes an application problem. Now this is not a problem that somebody asked him to solve in the literature. It's more or less a problem that he makes up in order to demonstrate his method. So he makes up this problem. It's a reasonable problem though, and he illustrates his method using that problem. So it's not really central to the influence of this paper. So nobody is going to take the results of section 2 of this paper and talk about how important it is for going forward. Because it's really kind of a made-up problem. But here's the problem. You have two populations, group 1 and group 2. Each population has an unknown frequency of an observable trait. So these are the unknown probabilities. We have a small number of observations. Like in the paper, it's less than 10. You have R samples from group 1 that have the trait, S samples from group 1 that don't have the trait, R prime samples from group 2 that have the trait, R S prime samples from group 2 that don't have the trait. The way you want to think about this is group 1 is a placebo group, or the way that helps me think about this. Group 1 is a placebo group, and group 2 is the experimental group. And the observable trait is whether or not someone becomes cured. So you administer a placebo to someone, and there's a certain frequency that that person will just get better on their own. You administer the treatment to someone in group 2, and there's an unknown probability that that person who got the treatment will get better. And our goal is to calculate the probability that the frequency of being cured in the experimental group is greater than the frequency of just being cured in the control group. So there's actually a lot of difficult math involved in this. I say difficult, it's obvious to Dr. Thompson, but section 3 is kind of like a call to action. Okay, so the first thing is he draws some connections between his work in section 2 and some other work that's going on. So Thompson defines this psi function, and he says, okay, our goal going forward is to make a big table of the values of this psi function so that medical researchers could reference this table so that they can decide, who to give treatment to and and how many people get treatment and how many people get control. He says it's equivalent, or having a table of values of the psi function is equivalent to having a table of estimates for Pearson's B function and I function. I'm not exactly sure what those are because I don't have Pearson's paper that Thompson is citing, but I have a strong hunch that B and I are what we would call today a beta distribution and an incomplete beta distribution. So these are probability distributions that now are considered classical distributions, and stats libraries have methods for sampling those distributions and generating all kinds of samples and getting graphs and stuff. But the idea of a beta function or a beta distribution was not a concept at the time that Thompson was doing this work. So in essence, you know, he says, hey, there's this new special function that we need to make tables for. And he wants other people to do all the work. You can't really blame him because he spent enough time doing this for values where the sum here of R, S, R prime, and S prime, the number of samples, is less than 10. And that's publishable work. So now we want to make a table for large numbers of R, S, R prime, and S prime. This is genuinely a lot of work for a lot of people. He's like calling people to do that. Okay, now a little bit of my commentary based on Thompson's words. So just kind of explaining a little bit. So reminding ourselves of the problem. Say we must treat n patients, and we have a number p between 0.5 and 1, which is our confidence that B is a better treatment than A. Below is Thompson's, number 3 is Thompson's method of choosing which patients get which treatment. Number 1 and number 2 are the ones we looked at before. There's a concept in decision theory called regret that I really don't want to get into. It wasn't a concept in Thompson's time, as far as I can tell. He doesn't mention it in the paper. But the idea is regret is what you get when you imagine that you are wrong. What's the likelihood that you're wrong, and how much damage have you done? So if we're wrong about this P, then we just gave n people the wrong treatment. And there's a 1 minus p chance that we've done that. So when we say all patients get treatment B, we have a n times 1 minus p regret. When we say half patients get A and half the patients get B, our regret, unsurprisingly, let's look at this. Half of the people, we gave treatment B. So if we were wrong, this is likelihood that we're wrong. Half the people got treatment A, and this is the likelihood that A is the worst treatment. If you factor out the 0.5 and then factor out the n, you're left with 1 minus p plus p. So the p cancels out in this case. So your regret with a 50-50 split is 0.5 n. Now, choose B with probability P. So you take your probability P and you use that to choose whether someone will get treatment A or treatment B. So if you believe 75% confidence that B is better, then new patient comes, you're gonna roll a 4-sided die, and 3 out of 4 of those will be treatment B, because you have 75% confidence. 1 of those is treatment A. So the second part is important here. Then after you give the treatment and observe, you update P. So Thompson points out a distinction between a permanent problem here with a permanent fact about everyone gets treatment B and a temporary fact about his treatment. So we say, okay, P of the people, 75% of the people are going to get treatment B. Here's the chance that B is wrong. 25% of the people are going to get treatment A. Here's the chance that treatment A is wrong. If we simplify that, we get 2np times 1 minus p. This is actually larger than giving everyone B. But Thompson draws a distinction. He says, this is worse temporarily. This one's worse forever. The right way you want to think about this is really, if you take the n out of these, what's left is the derivative of regret with respect to n. And here, P is a constant. And if you want to calculate how much damage you've done, you have a constant times the number of people. Here, P is a number that, as we take more samples, is going down, we hope. And so this is getting smaller and smaller and smaller as n gets larger. So that's the distinction there, is that Thompson acknowledges, hey, this is not as good a deal for the one patient who comes in. This is not a very good deal. He has a 25% chance, he or she has a 25% chance that I'm going to give him what I believe is the inferior treatment. It's kind of a raw deal. But in the long run, permanently, like if you look at till the end of time, the information we get out of doing this saves more people. Whereas here we have this permanent doubt that we have to factor in, we have to account for. It is a pretty raw deal for that one guy that walks in though, you know? Okay, so looking into section 2, here are some math bits. Now, here we imagine that we have two infinite populations, again, so that we can make sure that our method, to make sure that our method is really worth doing, we want an endless supply of people, so there's always a strong incentive to learn. Each population has an unknown frequency of trait, and we have some observations. We need this probability. We've gone through all this before. Thompson proves this theorem. This is that first wall of integrals that is obvious to him. But he proves this theorem that the probability that basically the experimental treatment is better than the control has this formula right here. And this formula, we have binomial coefficients, we have a sum, we have division. In principle, this problem is completely tractable. It's just, you know, plug in the numbers and crunch. In fact, it's very easy to write a computer program that's going to calculate this for you. In fact, we'll show it later. But in Thompson's day, you just couldn't do this for very large numbers. If you did do this, you'd have to do it once and then save the answer and then tell everybody about it. And so that's when people would write tables and then they'd refer to tables, right? We have this n and this n prime. That's just a convenience of notation. N is the total samples that we've seen from group 1. N prime is the total samples we've seen from group 2. Just to tighten this up a little bit. Let's go on a little bit more. Now, let's step back. So calculating is a very difficult problem. And Thompson gets this answer. This is the answer to his question. He gets it on page 3 or 4. And it's done, right? But the paper, the next several pages are all about efficiently calculating this. So this is kind of interesting. So now we're going to define some convenience notation. We're going to define this function psi, this function n, and this function d. And they have the same type of arguments that our experiment has. So we look at that. Let's see. N is exactly the numerator there. So probably n stands for numerator, I guess. D is exactly the denominator, and psi is numerator over denominator. So psi is the probability that we're interested in, just cast as a function, whereas here, this probability applies to a very particular problem where you have all of this page of stuff, explanation to say this. Here we just cast that formula as a function, and this is what we're going to make a table of, really of the n's and d's. Thompson then goes on to prove some recursive formulas for the d function and the n function. So we have here the d function is in terms of the d function for smaller arguments. The n function is in terms of the d function for some smaller arguments. And so now we have a recursive formula. And that's really why Pascal's triangle shows up in this paper. If you think of Pascal's triangle, the triangle is a table to help you calculate those n choose k numbers very quickly and recursively. And so Thompson's saying, hey, look, we're going to do the same thing for the d function and the n function. And he goes, I promise you guys it's not going to be that bad. So then he goes on to build the table for small values of r, s, r prime, and s prime. And he goes on to prove several identities which show up in the table, which allow you to write a smaller table. So you can swap some of the arguments and get the same answer. And so those identities are in the table so that we don't have to write as many rows. Let's take a look at the table now that we've have a concept for understanding it. No, that way. So here we have a short table of the n and a d functions. First bit are identities. So we say, okay, here are A, B, C, D. What if we swap? The only purpose of these A, B, C, Ds is to show what swaps we've done. So if we swap A and B, and we swap D and C, how can we calculate that in terms of something that's already on our table? Well, here's an identity that Thompson proved for doing that. What if we then, after swapping A, B, C, and D, put the DC over here and the BA over here? Then it's the same as if you hadn't done that swapping. So that doesn't need to be on the table. If you ever did math before computers, or engineering before computers, it's obviously not software engineering, but something like that, I am under the impression that you made use of a lot of tables like this. Nowadays, well, we still have those tables, they're in a calculator. Yeah, I doubt that your calculator actually calculates anything. It's really a book of tables. Maybe it calculates a few things, but if you have sine and cosine and things, I imagine that it's a bunch of tables, that it's not calculating. You could do it where it is calculating something, but I imagine it's just tables.
Truncated Taylor series.
Yeah, that's how.
I had to cosine.
Okay, well, I took a gamble and I was probably wrong. Anyway. So here we go up to N and D, where, let's see what we have, up to control group 5, experiment group 5, and we look at all the combinations of that number of samples, at least the ones that our identities don't get. We have N, we have D, and from this, we're able to calculate the probability we're interested in by taking N over D. All right, so let's do some programming. I'm going to sit down for this. Oh, well, go one more slide here. Okay, first thing is a couple things that we have today make this problem really, really easy. Probably at least making section 2 trivial. So, section 2 is not very interesting in light of we have computers and calculate N and D very quickly. We don't even need the recursive formula. We can just go straight from the formula in terms of the N choose K, right? So we had a couple different ways of calculating this probability. One is to you actually calculate these combinations and sum them up. And one way is to use recursive formulas. I implemented both, and I didn't really do a lot of testing, but the recursive formulas eventually come back to the binomial coefficients, which are recursive themselves. So I doubt that there's going to be a lot of gain by using the recursive formula, unless you're aggressively memoizing, but you can do that with binomial coefficients anyway, so I don't think it gives you anything. Stats libraries. So what Thompson is doing is essentially working out samples from beta distribution by hand. And what is a beta distribution? That's kind of a modern, it's like a classical probability distribution nowadays, but it's kind of modern. And here's the funny thing, a beta distribution is in a certain sense defined to be the answer to this type of question that Thompson is asking. And nowadays, if you want to answer that question, you say, okay, I'm going to load up my stats library and I'm going to pull a sample from beta distribution. And you couldn't, of course, you couldn't do that then. So that helps us. Another thing that helps us a lot is conjugate priors. So we're going to talk about that a little bit later. So I will table that for a moment. Let's look at some programs. So here we implement Thompson's psi function and the recursive version. So psi function takes 4 arguments here and gives us a double. And it's the n function, which you can't name something with a capital N in Haskell, so it's going to be lowercase. The n function over the d function of the same arguments for the n function, and write these as sums for the d function. What is the n function? It is exactly as Thompson's formula has it over here on the left. So the n function is a sum of 2 binomial coefficients. So I'm going to call those a left A and a right A, where left A is r plus r prime minus A, choose r, and here right A, s plus s prime, it's the same exact as right here. A from 0 to r prime, exactly the same as right here. And same for the d function. Here we have the definition of the d function. And we're going to implement it exactly how the paper says. The recursive formula versions, again, I implemented them, but I didn't really test them. But you can see here the n function, the recursive n function, is defined in terms of the recursive d function. And the recursive d function is defined in terms of smaller arguments for itself. Okay. This is now my stats library. So, I guess let's cure some patients. Okay. Here, we're going to use the stats library in this program called sampler. So in the sampler, we need a struct to hold our results. And our results are very simple. We have the number of placebo successes, that's R, number of placebo failures, that's the S, treatment successes, R prime, treatment failure is the S prime. And our results actually can be, we have a kind of a neutral result and we can smash them together. Okay, now we have a couple things that we can do to a patient and give them a placebo. This is going to have some kind of result, same shape as here, depending on whether or not the patient is cured or not. So that's why we have to do this in I/O. It's going to use randomness. We're going to take the placebo. What is a placebo? Something I imported from models, which is right here, and it's hidden for now. Okay. And we have the treatment. What is a treatment? Something that is also hidden from us. But placebo and treatment are very simple. You call placebo in order to determine whether or not someone who took the placebo is cured. You call treatment to determine whether or not someone who was given the treatment was cured. So that's right here. We call placebo, we see if someone was cured. It gives true or false with a certain unknown probability, the same problem that Thompson described. If they're cured, then we give this result. Why this result? 1 placebo success is what we just got. Otherwise, we get 1 placebo failure. And same with give treatment. Okay, likelihood simply takes our results and calls the psi function with those. Now sample is the interesting part here. Sample takes our results thus far and gives us a new result. To sample, we flip a biased coin. So biased coin, placebo and treatment are both implemented in terms of biased coin. We don't know what the bias is. But biased coin is like the function where we pass in a double between 0 and 1, and it's going to land heads with the probability that we passed in. So we pass in 0.9, it has a 0.9% chance of landing heads which we think true, actually. So we flip a biased coin with our likelihood. And that is whether or not we treat someone. If we treat them, we give them the treatment. That is going to give us a result. Otherwise, we give them the placebo. It's also going to give us a result. Now, to iterate this, we're simply going to, this is not too important, but what we're going to do is, let's see, down here. We call sample on the results that got passed in. And we recurse main loop, taking the results that were passed in plus the new result, and continue. So let's try this out. I forgot that this wasn't Haskell Club, so I apologize if anybody has trouble reading the code. So here we are. Let's make this a little bigger. Yes, okay. Results so far, 0 across the board. Patient comes in. Since we have no results, the likelihood that treatment is better placebo is simply 0.5. So we're going to flip a biased coin, although this is going to be an unbiased coin. See what we do. We gave them the placebo and we failed. So here is our results vector, 0, 1, 0, 0. Since we just used a placebo and it failed, we get from really deep down at its core from Bayes' theorem, but in principle, or in practice just calculating the psi function, a 0.66% chance that the treatment is better now. Why? Because the placebo failed. Also, look at this giant jump. It jumped 16 points. So it's kind of a lot. Let's treat the next patient. Gave him a placebo. We were more likely to give them the treatment, but we're still a certain amount likely to give them the placebo. And it failed, so the treatment's looking better and better and better. Pick the treatment. That was what was most likely. It failed. We lost some confidence in the treatment.
Nothing works.
Nothing works. These patients are, male pattern baldness. Male pattern baldness will never be cured. Okay, let's see. Pick the placebo. It gave a success. Look at this giant swing in our confidence. Placebo has demonstrably worked once. Treatment has never worked. So treatment's not looking so hot. Pick placebo, it failed. Swings some. Notice how large the swings are in our confidence. This is an artifact of having a small amount of data. As we get larger and larger bodies of data, we'll still swing up or down, but the swings will be much, much smaller. And the psi function automatically handles it for that. We don't implement anything special in this sampler other than it's using the psi function. Let's go a little bit more. Oh, this is not so good. Oh, these look good. Okay. Pick the treatment. Success. Now we have about 60% confidence in the treatment. Pick placebo. Failure. Yes. Now we have a point. Wait a second. Right. So this gets down to the ethics of the thing. So this is a weird thing about this. We assume that we have infinite patients coming from like a stream or something, right? The infinite stream of patients. If we have, suppose that we have 10 patients, and that's it. And after this, there are going to be no more patients that have this illness. And say we have a 90% confidence that the treatment is better. Are we seriously going to like pick one guy out and say, okay, you're going to get the control, everybody else gets the treatment? Absolutely not, because there's no one else to benefit from the knowledge we've gained. So really, very critical assumption here is that we have no end to the number of patients. But let's, yeah.
Compute some sort of bound, since we know we don't have infinite patients. You should have sort of about this many to make this work well. It seems like it'd be a useful number.
Thompson does not, but subsequent people who've worked on Thompson sampling have calculated the order magnitude of different algorithms. So people who work on the multi-arm bandit problem in general. Thompson sampling is one solution to a multi-arm bandit problem. And people who have worked on that subsequently calculate order bounds, like big O notation, in terms of n on the regret, which I haven't defined, but there's notion regret, of different algorithms. So, so that's about as close as we can get to an answer to that type of question. I don't think that there's going to be like an n, that, like a number of people where it's really worth it to say, okay, give everyone the better treatment, and or otherwise. There could, I mean, I don't know. I guess there could be, but you can definitely calculate the order magnitude of different algorithms. So.
I have a very bad intuition for probability, but it also seems very counterintuitive that the fact that a placebo didn't work would increase your confidence that the drug works.
Right. So as we look at, so this is not like a formal answer to that, but as we look at these, here's the important thing. Okay. We're not calculating the probability that the treatment works. So what are we calculating? Let's go back to the paper.
So the idea that if placebo is really bad, it's not a high bar to beat.
Yeah, we're calculating the likelihood that one unknown probability, that's the effectiveness of the treatment, exceeds another unknown, which is, yeah. So that is important, you're right. And this does not tell us that the treatment is particularly good. It only tells us, hey, based on this data, we have such and such confidence that the treatment is at least, is better, right? So that's a very good question, yeah. Let's keep helping people. Okay, treatment failed. Let's go a little bit further. Wow, okay, we went a little bit further, and we now have a 94% confidence in the treatment. So at this point, we've had 3 placebo successes and 8 placebo failures, 7 treatment successes and 13 treatment failures. I can see why we now have such a strong belief in the treatment. And here is what makes this Thompson sampling. The next patient that comes in is going to have a 94.7% chance of getting the treatment. But we're never going to completely eliminate the placebo. We're never going to completely eliminate an option. So let's go further a little bit. Not surprisingly, it got a little bit worse. So we have 27 to 25 versus 5 to 11. And we can keep going. Now that we have a large body of data, well, large, notice also that the swings are not nearly as high as they were before. Because now it's based on all of this evidence. One thing coming in is not that much evidence compared to all the rest. It has some effect, but not a huge effect. Also, look at the number of people who got treatment versus the number of people who got placebo. If we had done a 50-50 split, at this point, this is when we would be saying, shoot, why did we do that? Something like that. So that's the benefit over a 50-50 split that this gives. So let's take a look at our models and see what the reality is. The placebo has a 30% chance of working, and the the treatment has a 40% chance. And at the time we stopped here, we were 90% confident that the treatment was better. Of course, if you want to do proper Thompson sampling, you never stop and say, okay, now we're just going to do the treatment. You keep doing this forever. With the understanding that the more confident you get in the treatment, the fewer people are going to get shortchanged.
So you go into your doctor's office, you're like, Doc, I got cancer. Doc flips a coin.
Right. Yeah, I don't imagine that anybody.
Take this pill.
I don't imagine that anybody uses this for medical research in the way we're describing. Maybe for experimental design, but yeah, in practice, people are going to cut it off after a certain point. But where
0.0001% chance you get mercury to treat a cold or something.
Right. Exactly. Yeah. I mean, you can't eliminate it.
Doctors are actually prescribing them. There's been enough data, presumably. This wouldn't be as valid anymore.
Right. Well, that's the thing. Is it gets back to Thompson's original question, is like, how much is enough? Like he says kind of in the first paragraph, he says, you might say, oh, we don't have enough data, we need more data, oh, now we have enough. How much is enough? And so here, instead of answering that arbitrarily, okay, when we get 10,000 samples, that's enough. We're going to say, okay, after 10,000 samples, what's our confidence in the treatment? And if it's 99.9, then we're going to treat 99.9% of the people, going forward with the treatment. But yeah, I mean, there's always somebody that gets unlucky, so it's a little bit weird. Where this is used,
In the alternative, there's a small probability that everyone gets unlucky.
that's true, right. The alternative is a small probability that everyone is unlucky. Yeah, I mean, it's, it's a, realistically, I would imagine that some doctors, at a certain point, give their patients a choice, not in a blind trial, but after a certain while, I think doctor might say, okay, there's, such and such percent chance that this one works, but this one, 10%, go ahead and choose, or are you going to choose? And so I don't know, maybe it's not a meaningful choice. Okay, so where else is this used? In addition to being used in medical experiment design, as it was originally intended, this is a utilitarianist problem, right? We have an expected amount of utils from lots of different options, and we want, over time, to maximize our utils. So what's a good proxy for utils? The best proxy for utils that I know are dollars. And so this is used.
I was going to say Oreos.
Oreos? I like Oreos too, but Oreos are pretty good.
Dollars can buy Oreos.
Yeah. So this is used in online marketing. I have 5 different ads that I can show someone. I don't know what ad is better or what ad is worse. I don't know the expected payout for these different ads, but I have some belief in the payout of each ad. I don't want to just pick the one that I believe is best because I could be wrong. So we're going to choose an ad proportionally to our belief, much like this table. And then we're going to observe the result and update our belief. Let's do this actually with slot machines. So let's see, how are we on time? I want to explain conjugate priors, but I don't want to explain conjugate priors. But they're here, and it's okay. So one of the things that makes Thompson's job particularly hard in this paper is that we don't have the notion of a beta distribution worked out. A beta distribution is, or can be thought of as, defined so that it's the answer to Thompson's type of question, and now since it's all worked out, we can call it from a stats library. So conjugate priors are essentially something worked out to be the answer to these Bayesian inference problems, and they make Bayesian inference very convenient. Oh, this table got screwed up. Okay, so a Bernoulli distribution is a biased coin. And if we have a Bernoulli distribution that has an unknown bias, just like these experiments we were doing, then its conjugate prior, which is a distribution that we can put on our belief in P, is beta AB, where A is the number of successes we've seen and B is the number of failures. When it comes time to sample, we can use our stats library. We can take our body of data, use our stats library to call up a sample from this beta distribution very easily. And it calculates it for us. An exponential distribution is an inverse exponential curve with a parameter lambda. And if lambda is unknown to you, then a convenient way to model what lambda might be is to use a gamma distribution. And what makes it convenient is that the parameters of the gamma distribution are simply the number of observations and, well, the sum total that you have received from your exponential distribution in those observations. This will hopefully make a little more sense when we look at the application. So here, again, we have our competing goals. We want to choose the best option, even though we have limited knowledge. And we also want to improve our knowledge. And so Thompson sampling gives us a way to do this simultaneously. And it works on small numbers of samples. You know, even if you have a small number of sample, you can update your beliefs. So here is an algorithm for a bandit solver using Thompson sampling. So bandit solver, what is that? Well, it's a solver of this type of problem. We'll see the next slide. But basically, the algorithm is we have 5 different options. For each option, we have a belief about its value. That belief is expressed as a probability distribution, and we have stats libraries that allow us to sample those distributions. So for each option, take a sample from that probability distribution that models our belief. Choose the option that gets the highest sample. Now, think about like die rolling. Think about like in a role-playing game, like Dungeons and Dragons. Everybody has like some damage dice. Every different weapons have different damage dice. So you might have something where you roll a 4-sided die, and something else where you roll a 6-sided die. Or something where you roll 2 4-sided die, and something else where you roll 2 6-sided die. Obviously, the guy whose weapon does 2 6-sided die worth of damage is better in an objective sense. But there's still a chance that somebody who rolls 2 4-sided die will do better on any given roll than someone who rolls 2 6-sided die, right? So we have a model, which is basically kind of the algorithm for rolling these dice for every option. At the time we need to make a decision, we roll the dice for all our different options. The guy who gets the best die roll is who we choose. We choose it, we observe the outcome, and we use the outcome to update our belief, our model. And we continue.
It's the reinforcement learning for robotics. That's cool.
Is this a similar algorithm?
Yeah, like how you decide where the robot will go. It's interesting.
I would like to hear more about that. That sounds pretty cool. So let's, this is almost done, so let's go a little bit more. So here's our problem. We are going to pick Chumash Casino clean. So if we want to do a bandit algorithm, we need a set of arms. This is where we say a multi-arm bandit. So each slot machine has an arm that you pull. So we say those are our set of arms. That's the terminology. Our arms are the penny slots at Chumash Casino. A slot machine is a convenient analogy because it has an immediate observable feedback. With medical experiments, it's like you give someone medicine and then you have to watch them for a little while. Slot machine, instant feedback, so it's great for token examples like this. You either win or you lose. That sounds a lot like a Bernoulli distribution with an unknown parameter. If you win, how much do you win? Which is probably not best modeled by an exponential distribution, but we're going to use that because it's convenient. So now, once we have our arms, and once we know our feedback mechanism, we can start making models for the goodness of our arms. Every arm has a Bernoulli distribution with an unknown probability of winning or losing. For that unknown p, we model it with a beta distribution, starting out with 1 and 1. Those are kind of neutral parameters for a beta distribution, so no assumptions. Our exponential has an unknown lambda, and so we model that with not exactly a neutral gamma, but kind of close enough, 1, 1. And the nice thing is, in order to do this, we have to know what Bernoulli and exponential mean, because they're tied to our observable feedback, which is where this problem touches the real world. But we don't have to know what beta and gamma are. We just have to know, we have a stats library, so we can sample a beta and gamma if we want to. And we have this table that tells us the right parameters to use are number of successes, number of failures. For gamma, number of observations, and the sum total we have culled from this slot machine. So here is some, again, Haskell code. We have a model to keep track of those 4 numbers: successes, failures, observations, amount of money. Although one of them gets to double up. This wins also is our number of observations for our exponential distribution. If we win, we observe that we won, and we get a certain amount of money from that. We can take a model and we can sample it to get a random double. So to sample a model with a certain number of polls, certain number of wins, certain number of money, we sample our beta distribution, conveniently provided by our stats library, with number of successes and number of failures. We sample our gamma with the number of observations about our gamma and the total amount of money that we've gotten from our gamma. And once we get those two samples, we multiply them together. This gives us a random number. Also, our model can be conveniently, two models can be smashed together, so you could parallelize this. So if everybody gets in the car tonight, we could all keep track of our own wins, losses, and amount of money, and then at the end of the night we can smash them together. Okay, an ARM has a model and some extra stuff. This ... is where our code touches the real world. In our toy example, it's probably the location on the floor of where that slot machine is, on the casino floor, something like that. In more sophisticated problems, this ... is probably something that tells you how to pull an arm. So if it's advertisements, it's the content, the creative content for the ad. And pulling an arm is serving that ad, for instance. So when we pull an arm, we get a random model. We get, if we lose, so we pull the arm, no, we didn't get anything. Pulls, we get one pull, no wins, no money. If we win, we just did one pull, we got one win, and we got some amount of money. Select takes a list of arms and gives us one of them, and this is the sampling. What we do is we take our arms. For every arm, we sample the model that belongs to that arm, and I'm just packaging it with the arm for a kind of data pipeline just next, because we're going to take the max by the first argument of the pair. So we take the max, the guy with the max sample, and we take, now we have one pair, and we didn't really care what the sample was. We just wanted to roll all those dice and see who won. And so we take the actual arm that had the largest sample. And update. We have a model and an arm, and we get a new arm. So update, we have an incoming model and an arm. We're going to take our arm and we're going to replace the model with the new model, where a new model is just what we get by smashing the arm's original model with the incoming model. This is a little different from our medical trial before. In our medical trial, all our data was in one vector. Here, our data is in a separate vector for every option. But otherwise, it amounts to the same thing if you concatenate all of them. We have some initial arms. Our main loop is very similar to the main loop in our other program. And main calls main loop on the initial arms. So this will take our arms, it'll select one, we'll pull that arm and get an incoming model. We'll update that arm, we'll pull it off of our original list and then put the updated one in its place, and then we'll recurse. Here's a controlled flow diagram of this program. Start with initial arms. Our data here are the points, and then our functions are the arrows. So we start with some initial arms, we select a guy. So we have an arm, we pull it, we get an incoming model. Update really requires 2 arguments, so we take those, pass them to update. Main loop doesn't really take 2 arguments. I'm cheating a little, because we're going to take this, we're going to take the updated arm, and we're going to smash them together and then feed them to main loop. And we're going to repeat. And do this forever and ever. It gets better and better. So eventually, we find the slot machine that wins. which is probably none of them actually. Right, okay, so thank you very much for your attention. I'm interested in hearing questions and comments.
It's
Yeah.
It's not going to tell us if it's winning, but it'll tell us if it's better than the others, right?
This one will give us an idea of what the unknown p is and what the unknown lambda is for each of our slot machines. Whereas the psi function before is just comparing two unknowns. This is, in fact, a little bit better because we have all this machinery that people have conveniently kindly programmed for us. Yeah, so we get to ask a harder question, but it's because of all the work that implementers have done. So that's where this is a little bit better than just the problem tackled in the paper. So here are some references that you can look at. Of course, Wikipedia is a very big reference. Compendium of conjugate priors, if you want to do any kind of statistical machine learning, this is a convenient source. It's not peer-reviewed though, so I can't vouch for whether or not it's 100% accurate, but it is a nice starting point. And the inspiration for the bandit solver mostly comes from this paper right here from a couple of researchers that work at Yahoo. So anyway, yeah, and all the code and the presentation are all available on GitHub. So thank you very much.
Thank you.
I had a question for you.
Yeah.
So this works with like binary events, like it's either a win or a lose. Is there an extension of this to events that maybe fall along like the real numbers or something like that?
Right, so I'm glad you asked so that we can dive into this a little bit more because this is my favorite, this is my baby. So a Bernoulli distribution is a biased coin where you either win or you lose, and it has an unknown real number parameter, but still the event is win or lose. So this is convenient for checking those. The exponential here is actually a real number, a distribution on the real numbers. So if we look at a Bernoulli distribution, it is a discrete probability distribution where you really just have a certain certain chance of winning, certain chance of losing. This is Bernoulli P. This is the density function of a Bernoulli P distribution. And an exponential you have something kind of sort of like the probability of landing on any individual point, and you have a curve right here. And I put probability in quotes here because now, instead of two options, you have a real number line full of options, and if you want the probability that your sample is going to fall between two numbers, you integrate, and that's how you actually get a probability. So the height here is not the probability, but the area underneath, right? And so this works just as well for real valued distributions. They don't have to be simply binary events. And what makes it easy is somebody went out and worked out these conjugate priors. Yeah. Anything else?
So how big are those? How many pairs of conjugate priors are there? Let's look at.
Let's take a look. It's interesting. I like it.
This is like the foundation for autonomous cars. Like this is the kind of stuff that they teach you for machine learning for autonomous.
Do you know anybody who's hiring? But yeah, I'm not surprised because this is really, if you subscribe to the Bayesian interpretation of probabilities, then this is, in a certain sense, the logic of inductive reasoning. right? So, I mean, again, this is a very loaded statement, so it's not something you could prove or disprove. But yeah, so if you say, okay, well, I want to know something and I can't use deductive reasoning, I have to use inductive reasoning and kind of Bayes' theorem and the associated theory of probability that goes around with it, like probability of A given B, calculate it somehow is in a certain sense, it's like the logic that you can use for inductive reasoning. Again, loaded terminology. So here are some distributions. Bernoulli, binomial. Binomial distribution is repeated Bernoulli trials. So you say, okay, I want the probability of a certain number of successes and a certain number of failures if I flip 20 bias coins. Binomial distribution is that worked out for you and put into tables or nowadays in stats libraries. Negative binomial, I have no idea. Poisson. So for Bernoulli and binomial, the beta distribution ends up being their conjugate prior, and we have this interpretation of the hyperparameters. So what are the hyperparameters? The hyperparameters are the parameters of our beta distribution, which models the parameter of the Bernoulli distribution. Right. So we have the interpretation of the hyperparameters. We have Bernoulli and binomial are very much linked, so I'm not really surprised that beta is both of their conjugate priors. Poisson is gamma distribution. I don't see an exponential distribution. Here we go. Oh, because these are discrete. Right. Here, normal distribution. Normal distribution is its own conjugate prior, except I'm not sure about that because this is not filled in. This is weird. And for these, the hyperparameters get a little bit more complicated, but still kind of tractable.
I think intuitively normal should be its own. Because these are supposed to be like eigenfunctions. It's like a distribution that sort of maps to a distribution of a similar form, right?
I know some of those words, so yeah, I know exactly. No, I'm not discounting what you're saying, and I completely empathize with what you're saying. But your intuition for this has got to be better than mine because I don't have a lot of background in probability. And they hired me to do machine learning, so go fig. But I don't have the strongest background in probability, but what you're saying makes like grammatical sense to me based on what you're saying, right? No, like the eigen is an eigenfunction in where it is kind of a I don't want to say like self-similarity, but where it's you do a transformation, you get back itself. Yeah.
Basically monoid.
Yeah, exactly. Well, that's another thing about the conjugate priors. Right. So what really makes the conjugate priors easy to work with, at least the ones that we're working with in the token example, is that there's this monoidal structure on your observations. The shape of an incoming observation is the same shape as your summary information. You could take two records and smash them together. So you don't need a context in order to interpret a new result. Your new result stands on its own, and then you can just smash them together to get something, to get all of them together. So you don't have to know the state in order to interpret a new data. So it really is, it's a monoid structure on the data itself, which allows us to be fast and easy. When we get into some of these others, I don't know if that's the case anymore. Like the hyperparameters here are number of successes, number of failures. That's pretty easy. What are they here? It's block of text. So I don't know if that's something that's true in general of conjugate priors. I don't know it well enough, but it looks like it gets a little bit hairy the further into the weeds you go. Anything else? So not all probability distributions are going to have conjugate priors. All of the exponential family, and I only know this because I just read it right here on Wikipedia, all of the exponential family have conjugate priors. But when we go to do Bayesian inference in general, what makes this problem tractable is, and really getting the definition of conjugate priors, which I just skipped over, but now it's worth talking about, is we have two families of densities. So I'm going to say F, which has some parameter, and H, which has some parameter. So two families of probability densities. You have an X, which is distributed with F theta of X. So it's this kind of graph, where X here is like one possible sample. You have theta, which is distributed with H alpha, and you grab something from X. This is kind of a more advanced version of Bayes' theorem, which is used for Bayesian inference. But the basic idea is Bayes' theorem tells you what happens at a single point. Now you do it for every single t, kind of. Not quite exactly that, but not that simple, but something like that. So here is your density function for theta. This is your prior. Here is big capital L, which in the literature usually stands for likelihood. The likelihood of observing x naught, which we just observed, assuming that t is the correct parameter for our h function. And we get a new distribution here. We kind of multiply these together, we get a new distribution here. In general, if we just take two probability densities and multiply them together, there's no reason that the result we get needs to be a classical probability distribution. So it's not necessarily something that we can conveniently make a call to our library for. But with conjugate priors, the definition of conjugate priors is that if there exists a parameter alpha prime, so that this new density we get is still in the H family, the same family as our prior, then our family H is called a conjugate prior of the family F. And this is, so
one is a generalization of the other, is that?
So in our context, F is our Bernoulli with an unknown P. And H is something that we impose on the P in order to estimate it. So you say, okay, I don't know what the unknown parameter of F is. So I'm going to give it, what do I do if I don't know something? I'm going to give it a probability distribution. That's going to model my belief of where it lies. And if you smash these together using Bayes' theorem, and if the result falls back into the H family, which is your belief about the unknown parameter of F, then the family H is called a conjugate prior for the family F. So what this ensures, this is like a closure property, in that it ensures that, if we have a nice way of calculating the H's, in principle, we should have a nice way of calculating the posterior, our updated belief. And in general, if H is not a family of conjugate priors for F, then there's no reason that this function G has to be nice or has to be something that we could even get samples of. So that's...
But there's only one conjugate prior for a given distribution?
I think so. Not sure.
It's not clear from this definition.
Right,
Like that would make
right.
sense.
It's not true? Okay. So it's not true, totally not true. Any superset.
Oh no, not any superset.
Yeah, because if you start with a if you start with a prior, yeah. It's not obvious to me that it should be.
Okay.
Well, if you add one thing to the set and just take the closure on your updates, that should get you a new one.
Yeah, I think that's right. Yeah. Okay. So imagine that you have a family H, which is nice. It's conjugate prior for a family F. Throw one bad apple in there. Then you could, in principle, say, okay, now my family is going to be this enlarged closure of doing these updates. And so you have a larger family of conjugate priors. It's still a family of conjugate priors for F, but maybe it's not, you want a smaller family. So the question is there a minimal family of conjugate priors? And I don't know. It's not obvious to me if there should be or not. Yeah.
Is this related to EN algorithm? Or more sort of constrained form of it or something?
I'm not familiar with the term there.
Expectation maximization.
Expectation
It's a
maximization.
similar type of iterative process where you update the parameters, recompute values, feedback, update parameters. But I think it's more.
Yeah. So it sounds like a reinforcement learning algorithm. And so Thompson sampling is one example of a reinforcement algorithm. And I imagine that maybe expectation maximization is something that is also maybe a reinforcement learning algorithm, maybe also a bandit solver. I'm doing a cold reading here, so let's actually find something out. Method of maximum likelihood or maximum posterior. Okay, so what makes Thompson sampling a bandit solving algorithm in particular? So it is reinforcement learning. It's a bandit solving algorithm, so it solves the multi-arm bandit problem, which is, so you have row slot machines, is that we have to pay in order to get an observation. So that's kind of the, yeah, we have to, we choose a treatment for someone, that's a cost associated with that, or that's a sample that we're not going to get, we're not going to see, we're not going to be able to fork and see both paths, So, and the same if we pull a slot machine arm, we're not going to be able to fork and see all of the options. So it doesn't seem like this is a bandit solving algorithm, but I mean, I don't know, this is just looking at it cursory, I have no idea. So, but that's, so they could be related in the sense, like, I think almost all of your reinforcement learning is going to use Bayes' theorem. So they're related, at least I think in that sense of Bayes' theorem. And then they could be related with conjugate priors in the sense that if you want to make Bayes' theorem easy, you use conjugate priors. But I don't know if it's the same kind of thing in that where Thompson sampling is a bandit algorithm specifically. Yeah. So thank you all for your attention. I hope you enjoyed listening as much and asking questions as much as I enjoyed preparing the talk and giving the talk. Thank you very much. So this brings us to the paper that we're going to look at today on the likelihood that one unknown probability exceeds another in view of the evidence of two samples. Let's actually take a look at the paper real quick. So we have it in I think I said bioinformatica. It's biometrica. Let's see. Department of Pathology. So this is not a medical doctor, but someone who I think works a lot with medical doctors. I'm not quite sure what Dr. Thompson's credentials were, PhD or MD. But either way, he's fairly good at math. He's so good at math that obviously is one of his favorite words. So let's take a look at this. Obviously, we may write. Okay, Dr. Thompson, thank you. If you look at that and you kind of go, okay, what is going on here? That's, I don't blame you. None of this is obvious at all to me. But so we have some math. We'll go into this in more detail here. We have Pascal's triangle. Okay, I know what that is. And let's see, we'll keep going. We have these, we have this psi function, which is going to be important. We have an n function and a d function, which are both going to be important. We'll come back to. And we have this table of numbers. What do these numbers mean? We'll get back to that in a minute. And why it looks like there's a lot of work going into doing this. So what is behind all this work? We're going to answer that. Okay. So, back here. What is the purpose of Dr. Thompson's paper? So he starts out in the first paragraph saying, this paper is not centered upon the interpretation of particular data. So I get the idea that things in biometrica are usually about a particular study. And he says, this is all right, thank you for coming to Papers We Love LA. This is the first one we've had in a while. Thank you to Jake and Brainium for hosting and for giving me the opportunity to speak. My name is Daniel, and we're going to talk about a paper by W.R. Thompson on the likelihood that one unknown probability exceeds another in view of the evidence of two samples. So first thing, on the evidence of two samples sounds kind of ridiculously small, doesn't it? So that doesn't sound like a lot of samples. Another thing is, the likelihood that one unknown probability exceeds another. So two unknown probabilities, and we want the likelihood. Man, that also sounds like another probability. So we're measuring two probabilities with some third probability, something like that. This paper appeared in Bioinformatica in 1933, and so it's not the typical thing we do for Papers We Love. Typically, we do something for something in comp sci or something at least a little bit more recent, and this is 1933. So. I think I promised applications to machine learning, so they're got to be in here somewhere. So let's take a look. So let's talk about the problem that this paper purports to solve, okay? So the problem we have here is medical experiment design. Thompson was a medical researcher at Yale. And it's a basic, typical scenario. You have two potential treatments, call them A and B, and you're not certain which treatment is better in some observable sense. So you can say better as in you pick some trait, like say hair loss. It's not about a particular study. This is about a general interest in problems of research planning. So that's the problem we had before. How do we design a medical experiment? And he goes on to say, there can be no objection to the use of data, however meager. Think about the title, on the evidence of two samples. There can be no objection to the use of data, however meager, as a guide to action required before more data can be collected. This is a little bit iconoclastic because you say, okay, I'm going to base a decision on a small number of samples. That is not really accepted practice. So he goes on, says serious objection can otherwise be raised to an argument based upon a small number of observations. So serious objection can be raised when you base an argument on a small number of observations. But he goes on and says, indeed, the fact that such objections can never be eliminated entirely. You never get the confidence up to 100%. So such objections can never be eliminated entirely, no matter how great the number of observations, suggested the possible value of seeking other modes of operation than that of taking large number of observations before analysis or any attempt to direct our course. So that last phrase is the typical modus operandum. Okay, we're going to just split our people into two groups. We're going to split our patients into two groups. We're going to collect a shitload of data, and then we're going to go over that data, and then after we look at that, then we're going to decide what to do in the future. And he says, no, because you say you're doing this to solve the problem of small sample size, but how much is a big enough sample? This is arbitrary, right? So he says, there must be some other way, there must be some way that they deserve it. So you have those competing goals. So let's look at some solutions. Two kind of obvious solutions. All patients get treatment B. Another solution, half get treatment A, half get treatment B. So often this is what you'll see in clinical trials. You say, okay, half the patients are going to get placebo, half the patients are going to get the medicine. And then after a certain while, when I guess the doctors are satisfied, they say, okay, we're going to stop splitting people up, and then everybody's going to get treatment B if we think it's better at the end. So two problems with, or the problems with these, when you say all patients get treatment B, if that's what you decide, then you're just done. You've given up increasing your confidence. You're just done. And yet, here, if we had 75% confidence, that's still a 25% chance we're wrong. And I don't know about you, but 25% chance is a pretty big deal. 25 things that are 25% chance of going a certain way go that way 25% of the time. There's actually a lot of the time. I say that, and that's kind of a frequentist approach. So you say, okay, 25% of our patients this treatment's not going to work. But that's not what it means. The frequentist point of view doesn't actually work here, because you're giving all patients the inferior treatment if you're wrong. Not just 25% of them, but all patients. So there's a 25% chance that every patient from here until the end of time gets the wrong treatment. Splitting people up 50-50. Is this ethical? If you think that treatment B is better, shouldn't you be giving people treatment B? And when do you stop? When is your confidence high enough? Do you wait until your confidence is 90%, 95%, 99%? All of those are arbitrary numbers. Why not 99.9? Why not 80? So when do you stop? Something like that. And you want to say maybe prevent hair loss, you pick some criteria, and then you say, okay, now I'm going to measure better by which one prevents hair loss, more frequently. So something like that, but you pick some criteria for which you're going to measure better. And how do you decide which patients get which treatment? Two competing treatments. You don't know which is better. How do you decide which patient gets which patient? A typical example comes up when we do medical research that has placebos versus versus active ingredient drugs, actual medicine. And you might say, oh, well, why are we comparing a medicine against a placebo? And this is simply so that you can tell that the medicine does something, really. So these treatments don't have to be something like two different medicines. One could be a placebo, one could be a medicine. But you generally have two different groups of people that you're treating differently somehow. Maybe the people don't know what group they're in, but whatever. Two different groups of people that you're treating differently somehow. And you want to see which treatment is better by your criteria you care about. So here, this problem naturally has some competing goals that you have to balance. Let's suppose that we start out thinking that treatment B is better than treatment A, and we start out, say, at 75% confidence. We're 75% confident that treatment B is better than treatment A. How did we get that confidence? I don't care right now, just run with it for a moment. We have some competing goals when we decide what treatment to give to what patient. First goal is exploration, in which we hopefully want to improve this confidence. If treatment B really is better than treatment 1 in some objective sense, then we should be able to get this pretty close to 100%. But then we have a competing goal of exploitation. If we think that treatment B is better, why aren't we giving treatment B to everybody?